Today we continue from where we stopped last time. I need you to write your name and ID number for the attendance. Okay, so chapter 11 is talking about rolling contact bearing, as I mentioned. And in this course, we're not learning how to design the bearing, but we're learning how to select them. Remember, these bearings are standard elements. Putting here 3 bearings, they are all ball bearing. The corroded one is a double row bearing, just to show that you can have not only a single row, but you can have 2 rows of rolling elements side by side, in order to increase the load capacity of the bearing. Right. This is a cross cutaway in a ball bearing, just to show main important parts that builds the bearing. So as you can see, we have an outer ring. Okay, we have an inner ring. We have the rolling elements. Here in our case, these are ball bearings, so the rolling elements are ball. Now we have something holding the balls away from each other. We call them retainer or separating ring. So these are the main 4 components. So inner ring, outer ring, rolling element, and a retainer. Now cheap types of bearing, they do not come with a retainer. Okay, they can just have the inner ring, outer ring, and the balls or the rolling element inside. But the retainer has a very important job. So what do you think the job of the retainer inside the bearing?
Make them far from each other.
Make them far, isolate the rolling element. So what would happen if the bearings collide and move freely? What do you think would happen? So the shaft? Actually, they will damage each other. Huh? So when I have damaged balls, so imagine 2 balls, they come and collide, there will be some deformations. Huh? So now, do we have a smooth surface? Or we have a dent kind of thing? So now, as they roll now, start here. So like when you have a flat tire. When you have a flat tire, how does it work? Yeah, how does it move your car? It's jumping and a lot of vibration and so on. So the separator job is to keep an equal distance between the rolling element. And when I keep equal distance, I prevent them from the collision between each other. Secondly, I ensure a uniform distribution of load. So I don't have one side no balls and it's carrying all the load, and some part they have a lot of balls, they're sharing the load. Right. There are some geometrical dimensions that are very important. So the inner diameter of the bearing, we call it the bore. Okay? And the bore must match the shaft diameter, where you're going to fit the bearing. The place where you fit the bearing, the diameter of the shaft should be matching with the bore. Now there will be some interference in order to have what? Firm connection between the inner ring and the shaft, because those 2 should run together. No slip action should be happening. If there's a slip, it means there will be friction, heat develop, and whip.
Between again the
Shaft and the bearing. In this zone. Then we have the outside diameter. The outside diameter also determines the size of the bearing. So every time the outside diameter increases, means the rolling element inside size is bigger. Now, when you're designing a structure, there's some space limitation. So I cannot just pick the bearing based on its bore size, also the outer diameter, so it can fit in position. The width definitely is very important, as it's control also the stability of the shaft. When you increase the width of the bearing, okay, you give more rigidity to the shaft. You make it narrower, less rigidity to the shaft. It becomes flexible. If you remember in the machine the design 1, when you learned how to design the shaft, you first design it against fatigue. So. Then you check, after you define the geometry, all the diameters, you check the deflection. So. And you check the deflection at the gears location, you check the slope at the bearings, and so on. Now, if the deflection are exceeding the limit, what do? You change, how you change the design? You just stress. Change the diameter only. Do you change the material? You go with a harder steel, for example? No, it doesn't work. Why? Because deflection is based on modulus of elasticity and second moment of area, right? Flexural rigidity, we call it. Those two terms, you multiply them together. So it's based on flexural rigidity. Every time your modulus of elasticity increase, means the rigidity of the structure increase. You need more force to cause deformation. Huh? And every time the size increase, also becoming harder to deflect. Now, one other way is to increase support. So, if I have large deflection, adding more support will minimize this deflection. So increasing the width of the bearing is one reason, one way of increasing rigidity of the. Now, yes.
Not stable, you mean?
No, rigidity. So it's, I will not say stability, but to minimize the deflection under static load. Because there's deflection in few other reasons, by the way. As it's rotate, there's some dynamic loads, like imbalance forces. And these imbalance forces increase with the rotational speed. If you increase the speed, centrifugal forces increase, and the effect of imbalance on the deflection will increase. But in this course, we're looking only from the perspective of static loads. Right. There are other geometrical features in the bearings, like the fillet at the corners, and those are important when you design your shaft. If you remember, when you design the shaft, you start with an estimated fillet radius, correct? Mm-hmm. In order to calculate the stress concentration factor, you start with a certain fillet radius. Now, at the final stage, you need to make sure that the fillet radius of the shaft is matching the selected bearing. Otherwise, the face of the bearing cannot come in touch or in contact with the shoulder at the shaft. You remember, we used to make shoulders on the shaft for two purposes. Huh? What are these purposes? Now, we used to have stepped shafts, like this. Right? Why do you make these shoulders? Yes, we call it shoulders. Huh? We call them shoulders. Why do we make these shoulders? What's the job of the shoulder? There are two jobs for the shoulder. First job is the axial position. Now you are mounting, for example, a gear here. How the technician would know that the gear should be fit at this exact position? Yeah, what? Put the marker for him? He take the measurement? No, this is not true. It's not correct. So you need to have a physical constraint. So when he fit the gear, you slide the gear till the end, where the position. This is one. So axial positioning of stuff or elements mounted on the shaft. Second job is to transfer the thrust loads. So for example, if I have a helical gear here, okay, helical gear tends to induce thrust load. So this axial load, how can I transfer it to the bearings and to the structure? If there is no shoulder here, the gear will move with the load. So what holds the gear in position? The shoulders. Now the load will go transfer to the shoulder. So now the load will move from the gear to the shaft. Now what holds the shaft is the bearing. So you need another shoulder to transfer the loads from the shaft to the bearings. So now I have the bearings here, for example. The fillet radius we are talking about is this one. Now, if this fillet radius is very generous, I cannot fit the bearing till the end. So the face of the bearing will not touch the shoulder. So how am I going to transfer the load? Okay, so that is very important when you come to finalizing your geometry and dimensions. Now, how do we introduce the balls inside the bearing or the rollers inside the bearing? There are two techniques. One is by offsetting the inner ring from the outer ring. You make the most suitable space at the top. You feed the balls. Then you return the inner ring to the center, distribute the balls, and apply the retainer. But this mechanism or this technique in feeding the balls limit the number of balls inside the bearing. So I cannot introduce as many as I want balls inside the bearing because I have a space limitation. So I have only the space in top here to put the bearings, to put the rolling gear, space in top. Now there is another technique, we call it filling notch. So in the filled notch bearings, the idea is that after you do the first technique, introducing the bearing, you add more balls or more rolling element by pushing them inside the bearing. So you force them to go inside. But how can I force them? I need some space to force them. So that's why they make what they call a filling notch. Now if you look at the bearings you have here between hands, the space from the right face and the left face is the same. No filling notch. But with a filling notch, one face will have a bigger gap, okay, where we can introduce the ball by pushing them inside. But is there any advantage of increasing the number of balls inside the bearing? The bearing can take higher loads. Okay, so there's one advantage of taking higher. What kind of load? Thrust load or radial load? Radial load. But what will happen to the thrust load? Is it going to be the same or it's going to reduce? So his opinion is same. A bearing with a filling notch, can it carry larger thrust load, the same, or less thrust load compared to normal one? Same, same, larger, larger. Any idea? Are you following me in the back or disconnected? Everybody's disconnected. The answer, no, it is less. What comes by force goes by force, huh? Right? What comes by force goes by force. So, because I make this bigger space, so smaller constraint in the axial position, so I can force them to go inside. Now, if I apply a thrust load on them, they will go outside. Huh? So, the thrust load capacity for fill notch bearing is less. Because if I apply an axial load like this, what will happen? I'm going to push the balls back outside. And so, because the gap is big. But on the other hand, radial load capacity increases. But the type of bearings that we are discussing in chapter 11, there are three types of rolling elements we talked about: the ball, the cylindrical, and the tab. So these are showing the shape of the rolling element. What can you notice? When I have a ball, the contact is a point. So if I bring a ball and put it on the table, I have only point contact between the ball and the table. But if I have a cylindrical roller like this, the contact surface will be bigger now, and I will have a line contact. Same thing for tapered roller. So, due to the contact area, the radial load capacity for ball bearing is good, but for cylindrical and tapered is excellent. Why? because they have more contact area. Now, when I look at the thrust load, scenario is different. If I look at the cylindrical as poor or none, cylindrical roller bearing cannot carry thrust load. But for tapered roller bearing, it's very good, and the ball bearing is poor. Does that mean the ball bearing cannot carry thrust load? No, it can carry, but not very high thrust load. And the thrust load is not comparable to the radial load. Okay, and you can have a radial load of, let's say, 2,000 Newton, while the thrust load is in hundreds of Newton. Okay, ball bearing can take care of that.
Because what
The thrust is going to be in this direction, so the ball cannot orient itself 100% to take the thrust load. Okay, but for tapered roller bearing, because the rollers are inclined, the surface of contact is inclined, so it can carry the load. We'll do some sketches soon to show the difference. Now we'll start with the ball bearing. Just to identify the radial and thrust load, these are the loads. So radial load is perpendicular to the, or goes towards the center of the bearing. Thrust load is along the axis of the shaft. Now where we have applications, gears induce thrust load, manufacturing machines have thrust load. In the car, the wheels, front and rear wheel, they are all exposed to thrust load. So thrust load means it's along the axis of shaft. So this is direction of thrust load. Okay, radial load is the loads that are lateral to the shaft. So when I have such a design, okay, so we have a radial load and I have thrust load. Now one of the bearings should be responsible to carry the thrust load, while the radial load is going to be distributed in both. So ball bearing, they can carry both radial and thrust load, but the thrust load up to a certain level. They don't have high capacity for thrust load. Now we have two types of ball bearing in the book. There are others, but what we our problems in the book, they're mainly between those two types. We have deep groove ball bearing and angular contact ball bearing. Right. What's the difference? Now, if you look at the bearing, we have one that's open, huh? So you can see the inner ring and outer ring from inside. There's a groove where the balls can be rolling and constrained between the shoulders. Right. So the groove from inside looks something like this. So this is inner ring. This is outer ring. Okay? And the ball is inside. So deep groove will have a symmetric candy groove in the inner ring and outer ring. Now the second type, so put it deep, so deep groove. The second type is different. In the second type, the groove is not symmetric. So again, this is inner ring. This is outer. So what is the difference? This is angular contact. Here the ball, as it rolls, it can have contact between those 2 points, or a little bit shifted here or here, because the groove will not give it the freedom to roll at different axes. Okay, so the axis of rotation will maintain almost horizontal and parallel to the axis of rotation of the shaft. So if I have the shaft is here, this is axis of rotation of the shaft, and this is the axis of rotation of the ball. So it rotates about this axis. But in the angular contact, because I have bigger space here, the ball can roll about this axis. Yeah. So if I have a load combined load, thrust load and radial load. The thrust load will cause the ball to run at a different axis, roll at different axis. So instead of having contact here and there, we'll have a contact here and there. So it is, the axis of rotation is tilted. So by this, I can carry more thrust load. Because now the combined load, when I combine the thrust with the radial, will be always to these points, 2 points. So the ball can change its axis of rotation and carry the maximum load. Done. So angular ball bearing, they have higher thrust load capacity compared to the deep groove ball bearing, but in one direction. Why in one direction? I'll give you. This is, let's say, this is the angular contact ball bearing. And I have a thrust load coming from this side. And I'm holding the bearing from here. This is the housing. Now, when I push the inner ring like this, okay, what will happen to the ball? It will be squeezed with the shoulder here, huh? So in this case, the bearing can carry the load. The bearing can carry the load. Now let's reverse this scenario. And let me push from this side. What will happen? This will go out.
Yes.
So can the bearing carry the load now?
No.
Right. So in this case, whenever we select an angular ball bearing, we use them in pairs. Why? Because you never know, the direction of thrust load may change during operation. Like for example, if I have a helical gear, this exact example. Now, if the helical gear is running clockwise, it's different than when it's run counterclockwise. Imagine you have motion in both directions. The gear one time you make it running clockwise, and the second time you make it counterclockwise. So the direction of thrust force will change. So if I'm using angular contact ball bearing on one side, okay, during the first operation is carrying the load, but when I reverse the motion, the load is not going there, going to the other side. So you need to be careful when you use the angular contact. So this is summarize what I just said, talking about deep groove ball bearing, filming notch, and angular contact. Now, one of the issues when we deal with rotating equipment is the alignment. Have you heard about alignment? If you work with the co-op, if you work with the reliability people or maintenance. We have alignment in the car for the wheels, alignment of shafts. Now just to make the story simple, whenever I have two objects and something is connecting those two objects together, these two objects must be on one line, right? In order to maintain stability. So if I have a pump here, or a motor, this is a shaft of the motor, and I have a pump, this is the shaft of the pump. If those are not on the same line, I cannot couple them. And if I couple them by force, when they rotate, it will cause a lot of vibration. This is alignment between two shafts. This is one thing. Now what about bearing? Now let's look at this example. Now this bearing is not in the air, it's fixed to a structure, the bearing housings. And this one also is fixed to the bearing housing. Now, if the bearing housing here is not aligned with the bearing housing on the other side, what will happen? The shaft will remain straight or tilted? It will tilt. This is not possible. The shaft cannot tilt. It must be straight, either vertical or horizontal. I cannot make it tilt because it cannot deform. So I will make let's look at from top view. I have a bearing housing here. This is the center of the hole for the bearing. And it's supposed to be aligned with the bearing housing here, but there's a shift. This is the center. Now when I mount the shaft cannot go like this. The shaft is not flexible to bend this way. Okay? The shaft will go like this. Here will not be straight. Here will not be straight. Shaft will go something like this. Okay? So now here, if I have this is the inner ring. See, the inner ring will tilt with the shaft. The inner ring will tilt with the shaft. But the outer ring is straight horizontally with the housing. So what happens to the rolling element inside? It'll get damaged. So the life again becomes smaller and so on. Now, to overcome this issue, they came up with what is called self-aligning bearing. So self-aligning bearing, they compensate for the misalignment, either during manufacturing or assembly or so. By the way, self-aligning bearing usually tends to have a lower capacity as compared to deep groove or angular contact bearing. But they can compensate for misalignment, so it's a nice statement. We have two types of self-aligning. We have external self-aligning bearing, we have self-aligning bearing. In the external, there's an additional part that's going to be fixed to the housing. So if the housing is not aligned perfectly, the inner part of the outer ring will tilt. So the whole thing, this can tilt up and down. Okay? So if I have a misalignment like this one, so no problem. Both the inner ring and the outer ring will tilt while there's a stationary part here. This is the line you see in the Now for self-aligning bearing, without an external devising, the idea is that the groove is made wider. Okay, so the groove is wider. In this case, the rolling element inside has the freedom to go sideways. So if this is tilting like this, okay, the ball will go to the left, and still the stresses are almost uniform on the rolling element. And the same thing when it goes to the right. So self-aligning bearing, they can adapt up to 1 to 2 degrees of misalignment. So again, here also when we talk about misalignment, it's only about in 1 or 2 degrees. Okay? Now there are other types of bearings that are thrust bearing. We're not going to cover thrust bearing in this chapter, but now this is showing a kind of relative capacity between the types of bearing. The relative capacity is compared to a deep groove. So you can see a deep groove ball bearing is taking 1 as a capacity. Let's look for the filling notch. When you increase the number of balls inside, you can increase the capacity by 20 to 40%. But look at the thrust load. Let's drop it. If you look at the self-aligning bearing, you are losing load, but you are having good alignment. You can compensate for misalignment. Another option of increasing the capacity without increasing the radial size of the bearing is to use double roll, just like the bearing we have. So a double roll, look, it has increased about 50% in the capacity of the bearing, okay, as well as the thrust load has increased. But look at the misalignment tolerances. It's becoming small, almost zero, as compared to the heavy groove ball bearing. Now remember what we said about the when you increase the width of the bearing, you are adding more constraints on the shaft, you're increasing the rigidity of the shaft. So it's becoming tougher to deflect or make a slope there. The other type of bearing is the cylindrical roller bearing. So this is the cylindrical roller bearing, different types. Okay, the rolling element shape is different, but we talk about those two: straight or plain cylindrical roller bearing, and the tapered roller bearing. Those are the two types that we're studying in this chapter. Now, and as we said previously, that with the cylindrical roller bearing, the contact we have here is a line. So this brings a question: why straight roller bearing they have higher capacity as compared to ball bearing? The simple answer is contact. Surface contact with a straight cylindrical roller bearing is bigger. But with the ball bearing is smaller. Right. Let me draw a rolling straight roller element, straight cylindrical roller element, to understand some of the features of this type of bearings and limitations. I'll draw the shaft in red. So this is the shaft. This is the inner ring. This is the roller. And this is the arm. So the first point we said that cylindrical roller bearing, they have higher capacity for the radial load. And the reason? I have bigger surface contact. So, where's the direction of radial load? This is the radial load. Now the second point is saying that a straight roller bearing cannot take thrust load. Why? It will slide out. Let's look at, now here the radial load is perpendicular to the rolling contact surface, right? Now if I look at the thrust load, it is parallel. So what will happen? The roller will slide out rather than roll. Now if the rolling element is not rolling at the direction of load, it means it's not carrying the load. It will slide, start to slide. Another issue. How many curved surfaces do you have for a cylinder? It's only one curved surface. Huh? So these two surfaces here, 1 and 2, these are flat surfaces. Can they roll? No. So even if I make this bigger like that, the inner ring and outer ring, when I apply the load in this way, what will happen here at this state, this part? There will be rubbing, sliding. They start to rub, increasing temperature and failure. Therefore, this type of bearing carries no thrust load. The last part, this type of bearing requires perfect geometry. When we talk about perfect geometry, we're talking about alignment. Why does it require perfect alignment? Let's imagine that the shaft is tilted. Okay, now the inner ring goes with the shaft. Huh? What will happen to the roller? Is it going to remain straight like this?
No.
So what will happen is that the roller will be tilted, and this is the inner ring, and the outer ring remains straight. Here will be penetration of the roller inside the inner ring and outer ring, more rubbing. Stress distribution is not uniform on the roller. So all of these issues will result in dropping the life of the bearing and quick failure of the bearing. So the only single advantage of straight cylindrical roller is higher radial capacity. Okay? So in such a scenario, when I have combined load, the location where the bearing that is going to carry the thrust load, I shouldn't put cylindrical roller bearing. And the locations where we have high radial load, with zero thrust load, it's a wise decision to utilize the cylindrical roller bearing. Why? Because with a small size, I can hold the load. Another type of cylindrical roller bearing is called the needle bearing. We're not going to learn how to select these types because selection criteria is the same for all bearings. Just to give you an example and advantages of this type. Now again, this type cannot carry thrust load, just like the cylindrical roller bearing.
Previous slide, the other slide was the table.
Table after this one. The needle type is simply like the cylindrical roller bearing, but instead of using cylinder, plain cylinder, we are using cylinders with S, thin cylinders. The radius to the length is small. The radius of the cylinder, the length of the cylinder ratio, the ratio is small. Now, what's the beauty about this? Is the size. Okay, so the size is much smaller in terms of outer diameter. I'm talking.
So the inner ring and the outer have the similar difference.
Now, even if I'm using inner ring and outer ring, so this type of bearing, it can be with inner ring and outer ring, it can be with outer ring, it can be with inner ring only, it can be with nothing, just the roller and the retainer. So what builds the size, the outer side diameter of the bearing? Simply the roller size, thickness of the inner ring and outer ring. So if I get rid of the inner ring and outer ring, I reduce the outer diameter. So if I use small or thin rollers, I bring the outer diameter even smaller. So this is the advantage of the needle type bearings. It's usually utilized when we have size constraints on the radial dimensions. Okay, on the radial dimensions, it will help you in maintaining limited size. Now, if you want to use the roller alone without the inner ring and outer ring, there's further step must be taken. Now, if I'm going to mount the roller directly on the shaft, let me ask you a question. Which one is harder, roller or shaft? Which one has a higher hardness? Shaft or roller? Let's start from here. Shaft has the hardness of the shaft is bigger than the roller. Shaft hardness is higher. Shaft is higher. Shaft. في واحد حكى رولر وين؟ رولر hard. I know. Roller is hard. I have 3 said roller, and 3 are correct. The rest are wrong. Now remember, the roller. When we manufacture the roller, if they are made of steel, they are hardened because the roller will carry compressive loads. Okay? Why? This is why we call them bearing. Huh? Bearing stresses. Bearing stresses are compressive stress. Huh? Right. So the bearing, the rolling element inside should sustain high compressive load. When you say, imagine that this amount of load is distributed in a line or distributed in a point. There's a tremendous of stresses on the ball. Now, in order to make this steel very strong, you need to increase its hardness. Right. So now the roller hardness is larger than the shaft. So if I bring the hard material and fix it on the shaft now, what will happen to the shaft? As the roller starts to roll on it, start to cause damage. There will be wear, there will be scratches, and a lot of problem on the shaft. You lose part of the shaft material. So the step is as follows. You need to do surface hardening of this part of the shaft where you're going to mount the bearing, and then you mount it. you need to have a matching hardness between the rolling element and the surface of the shaft in order to minimize the amount of shear. This is to show the load capacity. You can see that the relative capacity of the rolling element, cylindrical rolling element, is about 1.55 of that of GB2 all there. Tapered roller bearing is the last thing we're going to study. Tapered roller bearing is simply a cylindrical bearing, but instead of mounted this way, we tilt it like this. Although it's not the exact cylinder, but this is the simplest way of presenting it. So what is the advantage of tilting the rollers inside the bearing? Let me remind you with the straight cylindrical. So this is the cylindrical. We said this is the line of contact, and this is the shaft. So we said that it can carry only radial load. The radial load is what? Perpendicular to the line. Now in tapered, where's the line of contact? It's inclined. So now if I have combined load, this is radial load and thrust load, can the bearing carry it? The answer is no. Or yes? Yeah. What do you think? Yes, because the combined load would be perpendicular to the surface. So it's still in the surface of rolling. So the advantage of, or the tapered roller bearing, combine the advantage of both cylindrical roller bearing to have high radial load capacity, because we have a line contact, and ball bearing that can carry combined load. So this is the tapered roller bearing. And tapered roller bearing actually has much higher thrust capacity as compared to the ball bearing. Now, other elements on the bearing, they are the shield or the seal. Okay, so the shields are usually metallic, and they are simply used to ensure that no foreign material goes inside the bearing, like the dust, for example. The seals, usually they are non-metallic, and their job is to prevent the foreign material from going inside, in addition to the foreign material in a liquid form or moisture form. So they prevent water or liquid, any fluid, to get inside. So these are the shapes. I think the one we circulate, one that is shield, I think, and one that the seals are removed. There are different types of bearings material. This is just a small table showing 4 different types of materials. General bearings are usually made out of steel or stainless steel, depending on the application. But some materials, some bearings are made out of ceramics. Okay, so when the temperature is very high, we usually utilize these ceramics. So we'll stop here, Shabab, and next time, inshallah, we start with the how.